So far we've discussed the simple gas laws, and I call them simple because if we combine them, we can actually get what we call is the ideal gas law. The ideal gas law, when gases follow the relationship that this law has between all the parameters, pressure, volume, temperature, moles, gases will be considered to have ideal behavior. And essentially what it is, like it said, when we combine all the laws that we've talked about, Boyle's law, Charles' law, and Avogadro's law specifically, we get the ideal gas law. Within this law, we have a constant. So this constant is listed right here. We call it R. Now you have to pay attention to the units that this constant has. So because this value has these units attached to it, that means whenever you use this law, the ideal gas law, to calculate any of your unknowns, you have to make sure that you convert all of your parameters to the correct unit. So for pressure, we have atmosphere, volume, liters, and obviously moles. And then for temperature, we're still using Kelvin. So here we have an example of what an ideal gas law problem can look like. So here we have methane is being considered for use as an alternative fuel to replace gas. 1 gallon of gas can be replaced by 655 grams of methane. What is the volume of this much methane at 25 degrees C and 745 torr? So for whenever you have one of these problems, you'll always be given 3 knowns. So let's see what we have. We have a temperature, right, 25 degrees. We have a pressure, 745 torr. We have a mass, but remember we can convert any mass to moles. So we will have the moles. And then we have obviously the constant right here. And we're searching for volume. So we are going to solve this. So we're going to isolate volume first. That's your first, that's what you should be getting out of the way essentially. And then we end up getting V equals nRT over P. So now that we know how we're going to solve this, we have volume isolated, right? Volume is our unknown. All we have to do is make sure everything's in the correct units, and then we just plug and chug. So 25 degrees C, we need to add 273 to that, and that gives us 298 Kelvin. As far as torr, we need to convert this using this conversion factor right here. So I'm going to do that. 760 torr gives us 1 ATM. So torr cancels out, and then we end up getting, so here I end up getting 0.980 ATM. And then next we need to convert our moles. So we're starting off with 655 grams of methane. We need to convert this to moles. And right here I have our molar mass. So grams cancel out, and then we get moles of CH4. We get 40.83 mole of methane. So now we finally have everything ready and in the correct units in order to plug in. So I'm going to write it in a different color. So now we have V equals our moles, 40.83 mole CH4 times the R constant times the temperature, which was 298 K, all divided by our pressure, which was 0.980 ATM. Make sure everything cancels, so we have mole canceling with this mole at the denominator. We have this Kelvin with this denominator canceling out, and then up here ATM. And then we're left with the volume, which is exactly what we want. And then when we calculate this out, we end up getting 1,018.8 liters of CH4. Now this is not in the correct stick fix, so actually we have to convert this to scientific notation, and then we end up getting liters. There is a set of conditions called standard conditions. At these conditions, we have a very specific temperature and pressure. So we call this STP. And the temperature is 0 degrees Celsius or 273 K. The pressure is 1 atm, or if you convert that to millimeters Hg or whatever other conversion, but it's always based off of 1 atm. Now at STP, if we calculate, like let's say we use these conditions and we calculate what the volume of a gas will be based on having just 1 mole, right? And these conditions, what will our volume be? So we plug everything in, 1 mole of the gas, we have our constant, we have 273 and 1 atm as our pressure. We get 22.4 liters. Now, what is interesting is that when you do this for any gas, regardless of what it is, because it's 1 mole, ideal gases actually have the same volume. So regardless of what type of gas, if it is at STP, whether it's helium, xenon, or methane, these are all different types of gases. If it is 1 mole at STP conditions, it will be 22.4 liters. The same for all of these over here. So we call this the standard molar volume, 22.4 liters per mole. So in the environment, we have like atmospheric gases, right? This is actually a mixture, and like many samples that we have of gases, we find that they're not just that one specific pure gas, it's usually a mixture. So in the atmosphere, we have 78% nitrogen, 21% oxygen. So because it's a mixture of these gases, which we assume behave ideally, we can actually use the ideal gas law and also the simple gas laws to measure and calculate certain whatever parameters we want, pressure, volume, temperature, as if it were like a pure substance and not a mixture. So Dalton's Law describes mixtures of gases, and essentially what happens whenever you have a mixture of a gas. So here we have a mixture composed of these individual gases. You're going to have a certain pressure associated with it, but that pressure is going to be made up of the individual pressures. So if we add all of these up, you will find that you get this value right here. So this is Dalton's law of partial pressures, where the total pressure is the sum of the individual pressures. So here we have a problem, specifically an example about how to use the partial pressures of a gas in order to determine an individual amount of moles of that gas, and then we can convert it to grams since the problem is asking for mass specifically. So this is our plan. We are given the total pressure right here. We are given the partial pressure of helium. We're given the partial pressure of neon. It's asking us to find information about argon, right? So essentially we need to first find the partial pressure of argon. Using that partial pressure, we're going to use the ideal gas law to determine moles of argon. With those moles, we can just use the molar mass, and then we can convert to grams of argon. So let's go ahead and find first that partial pressure. So we know P total equals our partial pressure, so helium plus neon plus argon. So first we need to solve for this algebraically. So we're going to subtract helium, and we're going to subtract neon from both sides. So then I'm going to get P argon, partial pressure of argon, is equal to total minus P helium minus P neon. So let's go ahead and plug that in. So we end up getting 662 minus, and then helium, which is 341, minus 112. And then we get from this 209 millimeters mercury. So we found the partial pressure of argon. Next, we need to use this partial pressure to solve for moles of argon. So we found the partial pressure of argon. And essentially now from here we can go ahead and find the moles. So we are going to isolate moles by dividing both sides by RT. And what we get from this is N equals P, the partial pressure of argon, times volume divided by R and T. Now, essentially, all we have to do is plug and chug. So we're going to make sure everything is in the correct units. And off the bat, I can tell something not in the correct unit is our pressure. So we need to convert this millimeters mercury to ATM. Everything else, for the most part, is pretty much set up. We have liters, Kelvin, and we have our constant. So all we need to do is convert that partial pressure. So I went ahead and set up my millimeters mercury, and then I got 0.275 ATM. So now we finally have everything ready in the correct units to plug into our equation right here. So I'm going to go ahead and plug everything in. So I went ahead and plugged everything in. Now I'm just going to make sure everything cancels. So my ATM cancels my liters, and then my Kelvin. Now what you're left with is, for the units at least, I'm going to show you, is 1 over 1 over mole for the units. Whenever you have a fraction as the denominator, what you end up getting is the inverse. So you'll end up getting mole as your unit, which is what we want. So now let's calculate this out in order to determine how many moles we have. So I got 0.016008. I'm just kept a bunch of sig figs, a mole of argon. And now our final step, so this was step number 2. Now our final step is to convert this to mass using the molar mass, which I have right here. So in 1 mole of argon, I have 39.94 grams argon. So moles cancel out, and what we get is 0.6393 grams argon. And I think everything on the previous page, well, we have our volume, which is only 2 sig figs, so this is going to limit our answer to be only 2 sig figs, so we would actually have to round this, so we would get 0.64 grams argon as our final answer. So as you learned in the previous chapter, we can use stoichiometry to get from, let's say, a mass of one thing, so let's say of a reactant. So mass of the reactant, we can get to moles of that reactant using the molar mass, and then we can get to moles, let's say, of a product using the stoichiometric factor from the chemical equation. From there, you can then go to mass, you can go to atoms. In this case, it's showing you mass, so you would take the molar mass of B versus A. Now we can actually do the same thing with gases using PV and RT. And the reason we can do that is because of the fact that in PV and RT, we have moles. So we can use that in order to determine moles, and then if we have the chemical equation, we can use the stoichiometric factor to get to, let's say, the product or whatever you need in the chemical equation. But we can use stoichiometry and also apply what we can calculate from the ideal gas law.